Hello again. In this segment, I will go over elementary stress in 2D and define the stress components. And then I will review the construction of Mohr Circle for stress transformations, which is a graphical method, and also develop the equations for the stress transformations that can be programmed or can be used on a calculator. And then we'll end it with an example to illustrate how we do stress transformations from one coordinate system to another. So let's first start with just a simple derivation of the equations for stress transformations in 2D. So let's look here at a situation where we have a element and this element has the shape of a small box like that, 2D, and it has the stress system that is illustrated here. So it has two stress components that are normal, and then we have shear components. So the shear, we're going to choose a different color, and the shear, we're going to put it on this face, on this face, on this face, and this face. And if we just have arrows, the shears, we're going to use single head for the arrows to indicate the directions of the shears. So the arrows will be in this fashion. So if in this case we have the x-axis is going this way and the y-axis is going this way, and this stress is sigma x, this stress is sigma y, and the shear is tau xy. It is on the x face in the y direction. This shear is tau yx because it is on the y face in the x direction. So that's kind of the convention for us for positive normal stress and positive shear. Now we're going to look at the same element, but we're going to cut it. So we're going to cut it across here and do equilibrium of the cut section. So the cut section is going to look like a triangle, like in this fashion. So the triangle now will have a force system on this face. So the force system on this face, we're going to call it tractions. So it will be a traction in the x direction and a traction in the y direction. And that force system will balance all of the stresses that we have on the other two faces that we did not cut. So if we have now that force system, we can call this P in the x direction and then P in the y direction, and this is again sigma y, tau xy, and this is sigma x, and this is tau xy. Notice that tau xy is equal to tau yx because of equilibrium of torques inside the material. And let's have this angle as theta, and then we have a normal direction to this inclined face, and the normal direction also is going to make an angle theta to the x direction. So our job is to now introduce a new coordinate system. One is going to be along the normal and one is along the tangent to the surface. So this new direction, I'm going to call it x prime, and this new direction, I'm going to call it y prime. Note that the x and the y are the old Cartesian coordinates. So what we would like to do is now find, so what we want to do is actually find some way to show the equilibrium of this system here that you can see on the side. So I would like to do the equilibrium of the tractions px and py with the stress system on the other two sides of this prism. So we would have to take the projections of all of the forces along the x direction and equate it to px, and take the projection along the y direction and equate it to py. The only thing that I need to be worried about is that I would like to make sure that I deal with forces and not with the stresses. So the force is the stress times the area. So let's kind of be careful and define the areas as we move on here. So if you look now at defining areas, if we take the thickness of this prism to be equal to 1 in the z direction, then the area would be just the length of each section. So the area of this is the length. Therefore, if I for some reason choose the length of the diagonal to be 1, this is the length, then the length of the element that is opposing theta or across from theta will be equal to sine theta, and the element that is right adjacent to theta will be cosine theta. So the area of the diagonal is 1, the area of the segment across from theta is sine theta, and the area of the segment that is adjacent theta is cosine theta. So let's take that into account, and now we write the equilibrium equation. The equilibrium equation in the x direction. The equilibrium equation in the x direction will be we can write it in this fashion. So p x times 1, because this is traction, it means that this is the force per unit area along the x direction. So the force per unit area times the area is equal to the stress, which is again a force per unit area, times the area that is acting on, which is cosine theta, plus we have to not to forget that we have tau xy that is acting on an area that is equal to sine theta. Same thing we can write for py will be equal to sigma y sine theta plus tau xy cosine theta. And now if I want to find the components of the stress along x prime, for example, then all what I have to do is project the p sub x along x prime and add to this the projection of p sub y along x prime. So I just bring him back to x prime, and that will give me the stress component along x prime. So let's do that. So if I just do projection, then the projection is going to be sigma along x prime is going to be p sub x and p sub x cosine theta plus p sub y sine theta. And then I substitute for p sub x with this quantity and p sub y with this quantity, then sigma along x prime is going to be sigma x cosine square theta plus sigma y sine square theta plus 2 tau xy sine theta cosine theta. And that is basically the transformation equation that we're looking for, transforming from the coordinate system x and y to a new coordinate system x prime and y prime. So this is one equation for x prime. Before we move on, I'm going to just simplify it by using identities, trig identities. So I'm going to use the trig identities that cosine square theta is equal to 1/2 1 plus cosine 2 theta, and sine square theta is equal to 1/2 1 minus cosine 2 theta, and sine theta cosine theta is 1/2 sine 2 theta. So if I do that and rearrange, I find that I can write sigma x prime as equal to 1/2 of sigma x plus sigma y plus 1/2 of sigma x minus sigma y times cosine 2 theta plus tau xy sine 2 theta. So that's manipulation of the previous equation, and I'm going to go one more step to manipulate this equation. We notice that we have here a term that I'm going to call C just for convenience, and then I have one term here times cosine, one term here times sine. Then I'm going to use a trick to change these terms using another triangular identity. So if I construct a triangle that looks like this, so if I just make a triangle, and this triangle, this is a made-up triangle, and this made-up triangle will have on it the components that will allow us to compute these quantities, and the made-up triangle will have on one side here, we're going to have 1/2 sigma x minus sigma y, and on this side we will have tau xy, and the diagonal of this triangle is r, and the angle here we're going to call it 2 theta p for convenience. So this radius or the diagonal is the square root of tau xy squared plus sigma x minus sigma y over 2 squared, and the angle tan 2 theta p is equal to tau xy over this amount, so it'll be 2 times tau xy over sigma x minus sigma y. And with these definitions, the previous equation, if you look at the previous equation, this amount here will be r, let me write it here, so this will be r cosine 2 theta p, and this amount will be r sine 2 theta p. And now you can see I can take r as a common factor, and I have cosine, cosine, sine, sine, and then I use a trig identity. Then I can rewrite the previous equation now in even a simpler form than before, and this simpler form is going to look like this. So I have sigma x prime will be equal to c plus r cosine and then 2 theta minus theta p, where now c is a constant and r is a constant, and theta p is an angle such that when theta is equal to theta p, we get the maximum of the cosine, which is 1. Therefore, we're going to sigma x prime will be maximum at theta equals theta p. Therefore, we're going to call theta p an angle of principal angle. So from that point on, we would just have theta p is equal to a principal angle, and it turned out to be that we have two of them, so the difference is that 90 degrees. So we're going to call this theta prime p, and then we have also theta double prime p is equal to theta prime p plus pi over 2. And we can do the same thing for sigma y, so I'm not going to rederive it, but it turned out to be that it's going to be equal to c minus r cosine 2 times theta minus theta p. And the same thing we can do for the shear at x prime y prime, and it is going to turn out to be r sine 2 theta minus theta p. So if you notice, if you take sigma y prime and tau x y prime together, you see that they can can be represented as a parametric curve, and the parametric curve, the parameter is theta, and it's obvious that the curve is a circle, and the circle has a center at C, and the radius of the circle is R. That's very simple. That's kind of the basis for Mohr circle, and therefore I can now construct Mohr circle by number one, a procedure. So the procedure is that we're going to establish a coordinate system here, like the horizontal is going to be for the normal stresses, whatever sigma x, y, sigma x, sigma y, and so forth. And the vertical is going to be for any shear. So I'm going to put the tau here. And then step one, then we find C as equal to the average of the stresses, normal stresses. And then we find 2 points on the circle. And point A is going to have the coordinates of sigma x and negative tau xy. Negative tau xy is the same as tau xy in the counterclockwise direction, because if you look at the element and then you have sigma x here, then the shear that comes with the sigma x is in the counterclockwise direction like this. So this shear is in the clockwise direction shear. So this will be in clockwise direction. Let's just make this here clockwise, because that's a shear that is affiliated with the sigma x. I better make this clear. The positive shear, so let me just go back and define positive shear. And the positive shear, as far as Mohr circle is concerned, is clockwise. That's the positive shear. So in this case, this is a positive shear. However, when we look at the element of sigma x, in reality, sigma x is going to have an element like this, and this element will have sigma x in this direction, and the shear is going to look like this. So that's in this case, the sigma x is associated with a shear that goes into the counterclockwise direction, which is a negative shear. So we'll take that back, and this will be counterclockwise. In other words, you have one point that has sigma x coordinates here and minus tau xy. The second point that we have, point B, will have the coordinates of sigma y and positive tau xy. Positive tau xy is, by our convention, is going to be clockwise. So we will have another point here. This is A and this is B. And now if we connect the A and B, that will be the diameter of the circle, and then the center of the circle will be the average value as we have in point number 1. And therefore, we can now draw the circle, the Mohr circle, and the Mohr circle will actually pass by the 2 points A and B, and it will intersect the sigma axis in 2 values of the principal stresses. This will be sigma 1, this is with sigma 2. These are the 2 principal stresses. And the angle of rotation from the x-axis, this is the x-axis here. Now if we rotate the x-axis in a counterclockwise direction, this angle here will be the 2 theta p, which is one of the 2 angles of the principal stresses. So that's kind of the procedure that we follow in constructing the Mohr circle. And what I would like to do now is, I did it all by hand. I'm going to go over some slides which show the Mohr circle construction and also the utilization of the 2 equations and an example. So let's do that here. This is a demonstration of the stress components. As I mentioned before, in 3D you have sigma x, which is normal to the x face. This is the x face here, and you have 2 shears, one on the x face. The first index is the face itself, x, and x here, and the second index is the direction of the stress. Y is the direction up, and z is the direction pointing towards u. So that's the case when we have the stress components. And now we have discussed how to the fact that the shears tau xy is equal to tau yx, because the cross shears are equal, because as a part of the equilibrium conditions, and therefore we derive these 2 equations that we have a sigma. This is a different form of what you've seen. What I presented is a simpler form, but this still works because this is your C, and this is the R cosine 2 theta p, and this is the R sine 2 theta p. And you can use equation 3.8 and 3.9 on the calculator to make the transformations from the old system, which is given by the stress acting on the y face and the stress acting on the x face, to the new system, which is the stress acting on the inclined face. Here you use the angle phi, and this is the normal to the surface. Either way is fine, and this is the angle calculation of 2 theta tan 2 theta p from the triangle that I showed you, and these are the magnitudes of the 2 principal stresses, which is C plus or minus R. So if you look at the magnitude of the 2 principal stresses, we have actually C plus or minus R that we can actually use. So we have now summarized here, the sigma 1 will be equal to C plus R, sigma 2 will be equal to C minus R. These are the 2 principal stresses, and tau max, the maximum shear, is the radius of the circle, R, and 2 theta p prime is 10 minus 1 tau xy times 2 over sigma x minus sigma y. So that's kind of gives us all of the information that we need to do the calculations. So having done that, then we can now take maybe an example to work on. So let's make the summary here, this summary. And now this is a nicer graphical representation that you can see. And the graphical representation shows you the Mohr circle. So the Mohr circle is right here. This is the center, C, which is the average value. This is the radius R, which is the magnitude of the hypotenuse, as we discussed. And this point A is sigma x and minus tau. Minus tau is the value of tau in the counterclockwise direction. And because counterclockwise is a negative, clockwise is a positive. So we would have A and B, and therefore, if we just take xy, this is the xy axis, rotated, physically rotated on the Mohr circle 2 theta p, it means that the element in reality rotates by an angle of theta p counterclockwise. If we want the stresses at a different orientation, for example, at any phi, at point H, for example, here, going to this, then we could use the Mohr circle to find the corresponding shear and the corresponding sigma 1 and sigma 2. So that's kind of a summary, and let's see if we have an example. So in this example, we have the element has sigma x equals 80 and no sigma y. So sigma y is 0. And it has a shear of 50 clockwise. 50 clockwise means it's going down. And going down on the right face means negative, because it is going into the negative y direction while it's on a positive x face. That's the convention that we have. So this is a negative 50. So the coordinates of point A will be the coordinates of 80 and negative 50, which means it's positive 50. Because remember, it is sigma x and negative sigma y, tau xy. So here we have sigma x and then a negative of a negative shear, so it makes it positive 50. And the coordinates of point B is sigma y, which is 0, and tau xy is in the counterclockwise direction, which is positive 50. So we can actually show that, and what's required from us is that we want to draw the Mohr circle, and then we want to draw the element correctly aligned with respect to xy coordinates, and we want to draw the stresses and show the principal shears tau 1 and tau 2 and the corresponding normal stresses and so forth. So it's a very complete example. And then B is we want to repeat the graphical way using the equations alone. So if you can see here, first is the coordinates A and the coordinates of B, and then we draw the line. So if I just first I need to find C, which is the center of the circle, and I need to find, which is now C is equal to sigma x plus sigma y over 2, that's 40. And I need to find the radius. The radius is the same as the shear, and that is the square root of sigma x minus sigma y over 2 squared, and then plus tau squared. That gives me 64. That's the radius of the circle. And I need to find the 2 theta p, 10 minus 1, and then I find it to be 51.3. So with that in hand, I'm able to draw the circle. Notice that point A flipped over to the top because the 50 is clockwise, which is positive in our convention here for Mohr circle. So the diameter becomes AB, as you can see here. The center is at a distance of 40 from the origin of the coordinates, and the radius of the circle is 64, and then this is the angle 2 theta p. Notice if I want to find sigma 1, sigma 2, I have to take the x, y axis and rotate it to the horizontal. So this has to rotate to the sigma axis to give me sigma 1 at this point and sigma 2. The rotation angle is 2 theta p, or 51.3 clockwise. So the physical element will have to rotate by half of this angle also in the clockwise direction. So if you look at the result, this is half of the angle, 25.7, rotated in a clockwise direction. And on that element, I have now sigma 1 is r plus c, sigma 2 is r minus c. And it turned out to be compressive, so its compression is negative. Next, if I want to find the maximum shear. So the maximum shear, if I go back to this, to find the maximum shear, I have to rotate point A to point E, and point B to point F. In other words, I must rotate by an angle on the Mohr circle of 38.7 counterclockwise, and physically the corresponding element will have to rotate by half of this, 19.3 clockwise. And when that happens, then the new stress state is completely dictated by the diameter of the circle when it lands on point E and F, meaning that sigma x will be equal to sigma y will be equal to 40, and the shear would be its maximum value, which is 64. So in this case, I can draw the element, and I have sigma x and sigma y equals 40, and the shear is equal to 64, and it's in this case positive shear, negative shear, because going down on a positive face. So it would be minus 64 and plus 64 on the y face. If I want to do now the same job with the equations, I can use the 10 minus 1 formula, find phi sub p, get the same number, and notice that we get two answers. The first answer, we add 90 degrees to it. And once we get that, we can find now sigma using the same formula, or the other one that I showed you before, the equivalent. And also I can find the shear to be 0 in here. Therefore, it tells us that these are the principal stresses. I can continue now to compute the shear. So if I rotate now, I find the shear angle. The angle for maximum shear is 1/2, and is the inverse of the angle 10 minus 1 of the angle for the principal stresses. In other words, the shear is the principal, the value of the maximum shear is obtained when I rotate physically 45 degrees away from one of the principal directions, which means, as in terms of Mohr circle, it would be 90 degrees away, and that means it's the inverse of the angle that we obtained before with a negative sign. So that's 10 minus 1, this value, the negative, and I get the same answer, 19.3, and then I add 90 degrees to that to get the second angle. And that completes the example, and the summary is shown here on the Mohr circle completely. And then this is the original orientation, this is in the principal stress orientation, and finally this is in the maximum shear orientation. And with that, I think we have completed a very good example on stress transformations, and we obtained all of the values of the stresses either graphically or with the use of the equations.